my student, principal of your college, for giving me this opportunity. I hope chemistry participants, do you have any idea about how many chemistry participants are there?
I think so 3 members, madam.
Acha. Okay, no problem. But actually, I have taken an overview. So I think everybody can understand this applications of computational chemistry in drug discovery. Why I have chosen this topic? Because now we are facing COVID-19. It's a global challenge. It demands the dire necessity of drugs. The one and only drug which is approved is remdesivir by FDA. So we need drugs within a short period of time. So for that matter, here the computational chemistry comes into the picture. So whereas in conventional discovery, what we do, it's a challenging process, time consuming and expensive, because we synthesize drugs in laboratories, one drug in laboratory, one drug, one day. Screening also takes place, a lot of time, spectral studies, all that. Even if we synthesize and it will come into the market, it takes a long-term process and it costs billions of dollars. So whereas computational chemistry is a branch of chemistry that uses computer simulations to assist in solving complex chemical problems. It includes a range of theoretical approaches to approximating the solutions of so all that computational chemistry involves the high power use of computers and mathematical equations for the purpose of predicting electronic, structural and spectroscopic properties of the molecules. So this is the very effective and indispensable tool. Why? Because I will tell. So because we can reduce the number of ligands that need to be synthesized, because it is a cost effective and less time consuming, because we prepare only the selected compounds which are active in computational studies that we perform. What are the computational studies? In the future slides, I will talk about. So only selected active compounds we will synthesize and screen. And this is complementary approach to HTS. What is HTS? High throughput screening. Actually, this high throughput screening is developed because of combinatorial chemistry. Combinatorial chemistry means synthesizing a library of compounds. So when we synthesize a library, a set of compounds in a single day, for that you require to screen that library. The HTS came into the picture. But that HTS and combinatorial chemistry also takes a lot of money. We have to use the equipment and all that. Plus time is also required. But whereas HTS is replaced by virtual HTS. So because COVID, even though COVID is a global challenge, we found the opportunities in challenge. So that's why we are in online teaching process. We are online webinars and here virtual HTS. In recent study of CAD, it was found that by introducing triphenyl phosphine group into the base molecule pyridoxine, it is possible to obtain inhibitors for proteasome. Further, analog synthesized this starting structure showed high potency. So this thereby influenced the development of novel therapeutics. So earlier slide, I want to show this. This is the schematic overview of representative of CAD process. So computer aided drug discovery. For that, we need to identify the target. If you know the target structure, we will proceed by structure-based drug design. If we do not know the target structure means here 3D structure. If we do not know the target structure, 3D structure, then we will proceed by ligand-based drug design. Under structure-based drug design, there are two approaches: high throughput docking, de novo ligand design. Under ligand-based drug design, three approaches are there: QSAR, pharmacophore mapping, similarity searches. Through these approaches, we will get the hits. Hits that are nothing but they are drug-like substances. So leads, we have to optimize that. The optimize, how we will do the optimize? By bioavailability studies. That is also performed in computers. So finally, we will get to the drugs, virtual drugs actually. Then we will go for in vitro verification. Finally, the process of clinical trials anyway remains the same in computational also. Why it is not going? What happened?
Madam,
It's not moving slide.
it's from your side only, madam.
Yeah.
Can you use your arrow
Yeah.
marks, madam?
Yeah. So this is, I said, structure-based drug discovery and ligand-based. The only difference between the structure-based and ligand-based is where we know in structure-based the three-dimensional structure of the target. In ligand-based, we don't know the structure of three-dimensional structure of target. So under structure-based drug discovery, so if we want to know the three-dimensional structure, how we will determine by experimentally, either by X-ray crystallography or proton NMR. And the second option is computational methods such as homology modeling. Why we need three-dimensional structure? Why we need means for using structure-based tools such as high throughput screening and direct docking methods on targets and possible drug molecules. The affinity of the molecules to the targets can be evaluated by computing various estimates of binding free energies. So after doing the docking and binding affinity evaluated, then optimization is done and the lead molecules will be selected for their in vitro activity. So I already said the two approaches: molecular docking approach, de novo, ligand design. Under the scheme overview I have given, and there is a word: molecular dynamics simulations are frequently used in SBDD to give insights not only how ligands bind with the target protease, but also the pathways of interaction and to account for target flexibility. So this is the application. HIV protease inhibitors. HIV protease is a prime target for AIDS. So under this, saquinavir, amprinavir. These are the structure-based molecular docking obtained, developed in 1990s. Saquinavir is the prime, first targeted HIV protease drug. In another study, SBDD methods have been used to predict the binding sites which are important inhibitor binding in AMP-C beta lactamase and experimentally verified. And this is also FDA approved. The one more application is dorzolamide. This is a carbonic anhydrase inhibitor used for glaucoma treatment. These are the applications, successful applications. So this is the simple flow chart in structure-based drug design. What we will do, first we determine the 3D structure of the target. Then we will do the molecular modeling by analyzing the physicochemical properties. Then after analyzing the properties, we will store, after the determination of 3D structure and analyzing the properties, we'll store the drugs. The drugs will be stored in database, and from that suitable molecules will be searched and bind with the target structure and studied the analysis of interaction. Then finally comes lead optimization. So, but anyway, X-ray crystallography is there, proton NMR spectroscopy is there,